Welcome to this lecture in the ongoing series of lectures in real analysis. Today we will be looking at the fundamental theorem of calculus, which is a beautiful theorem in mathematics. Last time we discussed the algebra of Riemann integrability. Primarily what we showed was that if f and g are two Riemann integrable functions defined on the same domain, then their sum and their product are also Riemann integrable. We also saw that restrictions of Riemann integrable functions are Riemann integrable. Alright. Let us also recall some other results that we need for this lecture, which we proved previously, prior to the previous lecture. So one such result is the following. So if f and g are bounded functions, with f being less than g pointwise, then the upper integral of f is at most the upper integral of g. And this is the proof. And same for lower integrals. Alright. And then there is this other result which says that suppose you have a continuous function which is differentiable on this open interval such that the derivative vanishes everywhere, then the function in fact is constant. So of course constant functions have this property, but the converse is also true, and the proof is an immediate application of the Lagrange's mean value theorem. One more result we will need is that if f is a bounded function and c is some interior point, then the upper integral or the lower integral can be broken apart into two parts, which is given by these formulas. And this is an immediate application of Darbo's theorem. Let us also look at the problems, because we will also be using these problems in today's lecture. So the first thing, okay, this one we won't use, but we will use the remaining two. The first one says that suppose you have two Riemann integrable functions, then we have proved last time that f plus g is also Riemann integrable, so it makes sense to ask what this value is. And indeed it is the obvious guess that it should be, and it turns out to be the sum of the Riemann integrals of f and g. And this is not at all hard, because this is more or less the complete proof of it. Okay, another thing is that suppose you have a bounded function, not necessarily Riemann integrable, just a bounded function, and alpha is some real number, then the upper integral of f minus alpha. And what is f minus alpha? F minus alpha is the function going from here to here, which takes x to fx minus alpha. So this is just a notation for this function, and it was, I'm sure, already clear, but anyway. So what this problem asks to prove is that this upper integral is the sum of the upper integral of f, or not the sum, but the difference of the upper integral of f and this quantity, which is nothing but the upper integral of alpha being the constant function alpha. So I'm not saying that in general you can apply. In general, we can't say that the upper integral of the sum of two functions is the sum of the upper integrals of the two functions, but in this very special case where one guy is constant, you can indeed just do the kind of linearity. You can play the linearity here. Anyway, so this is the theorem, and or rather the problem, and you can easily prove it. Alright, and one more thing is that suppose you have a bounded function, then the absolute value of the upper integral is at most the upper integral of the absolute value, and we'll use this today, and the proof is this. Since we mentioned the pointwise domination, this result, this one, using that we know that this pointwise inequality gives us that, and this pointwise inequality gives us that. So if you combine these two things, you get that. So this is more or less the complete proof for this problem. But anyway, write down all the details. That definitely makes things clearer. Alright, so now let us get into the material of this lecture. So here is the first thing that we want to prove. This is kind of the main lemma in the proof of the fundamental theorem of calculus. So what do we have? We have a bounded function, and we define two new functions out of that bounded function. The first one we are calling f, and the other one h. So capital F, capital H, and this is how they are defined. So for each x, you just integrate f from little a to x. So this is for all x in a comma b. In fact, I can put a closed interval there. So far it has been defined that way, but let me put a closed bracket here with the convention that this and that are 0. So with that convention, we have defined f from the entirety of this domain to real numbers. And this is called the upper indefinite integral, or the indefinite upper integral, and similarly this is called the indefinite lower integral. So out of f we can develop two functions, the indefinite upper integral of f and the indefinite lower integral of f. Okay, and this is a very useful convention, so keep this in mind. And this is not a disturbing convention, this is not an odd convention, this is a natural convention. The reason I'm calling this a convention is because this really does not, whatever we developed about the theory of integration does not really make sense for intervals which are degenerate, meaning where b equals a. So that's the only reason I'm calling it a convention. But even then I perhaps think that you can probably make sense of it even without much force. So but anyway, I will treat this as a convention. Okay, so here is the first thing that we want to prove. So we have again a bounded function and we have an interior point, and assume that f is right continuous at c. So with that hypothesis we want to show that the indefinite upper and lower integrals are right differentiable at c, not just continuous but right differentiable at the point c, and in fact their right derivatives are given by this formula. So the right derivative of f, of capital F at c, is small f of c. So all these right continuous, right differentiable makes it look more technical than it should be. So what one could also say is that suppose f were continuous at c, then the conclusion would be that f and h are differentiable at c, with the derivative being equal to that value. So the obvious variants hold, and I won't be writing them, but I will assume that you have them in your mind at the very least. Alright, so let's prove this. So what do we want to show? We want to show that, so basically we'll only do this part, that the right derivative of f at c exists and is equal to that value. So what we want to do is the following precisely, that for all epsilon, okay, so fix epsilon greater than 0, we want to show that there exists delta greater than 0 such that whenever h is in this right deleted delta neighborhood of c, we have this ratio is less than epsilon. So this will prove the right differentiability of capital F, and in fact it will show that the right derivative is nothing but that. So it will prove the existence and the value simultaneously. Alright, so we will look at this expression and see what we can do with it. So now this expression, just give me a moment. Yeah. This upon h minus f of c is by definition equal to a c plus h upper integral minus a c upper integral minus f of c, which is equal to, so note this step, this is equal to c plus h upper integral f So here this is equal to that, and here we used one of the things that we just recalled, that the upper integral you can break apart into two parts. So this upper integral you can break apart as a sum of that, and therefore the difference is that. So we recalled this in the beginning of this lecture. Okay, we have that much, but now we have this upper integral minus h times f of c divided by h, and here we'll play a little bit of a trick. So what we will do is, sorry, I forgot to write the f. Here we have an f. So h of fc we will write as this integral, this upper integral in fact. So fc is a constant, fc is just a number, so you can think of this as the constant function which we are integrating from c to c plus h, or rather taking the upper integral of it. And that is nothing but that. So we just played that much of an algebra, or whatever you want to call it. So we have that. But now we will use that third problem. Or was it the second problem? It was the second problem, this one. So we will use this problem to, basically write that quantity as this quantity. So using that problem, what we get is that this thing is equal to integral c plus h f minus f of c, that function, divided by h. Okay, so we have some kind of a little bit better handle on this. And now we will use continuity, right continuity of f. We have some epsilon greater than 0 by right continuity of f at c. There is delta greater than 0 such that whenever h is in this right delta neighborhood of c, we have f of c plus h minus f of c. Okay, let me not write h because that might get confusing. Let me write x, c plus x. In fact, if I've written x that way, then there is no c plus x, it's just f of x. So we have this, and this is immediately from the right continuity. This is same as saying that if you have, same as saying that 0 less than equal to t less than delta implies f of c plus t minus f of c less than epsilon. So both the statements are the same. Yeah, so we are interested in estimating that. So for therefore, if 0 is less than h is less than delta, we have the absolute value of f of c plus h minus f of c minus fc. This is equal to absolute value of c to c plus h upper integral f minus f of c divided by h. So here there should be a 0. I messed up, so please note here instead of a 0 I wrote a c, but it should be a 0. Okay, so far nothing. I mean, this implies this is equal to that, so there is nothing that we have done so far. But this thing is less than equal to integral c to c plus h absolute value of f minus f of c, and here we are using the third problem. So we have used the third problem when we estimate this with that. Okay, but now look at this function f of f minus f of c. This function, if you look at this line, is at most epsilon, in fact strictly less than epsilon, in this entire closed interval c to c plus h. In this entire closed interval, or maybe just in the open interval, doesn't really matter, c to c plus h, in this entire open interval, this function is less than epsilon. So this upper integral will also be less than epsilon, or less than equal to epsilon. So this is less than equal to epsilon h, because this is at most epsilon through and through. So we can estimate this by epsilon. This is less than equal to epsilon in throughout this interval, and therefore by the pointwise domination theorem of upper integrals that we recalled, this thing, this guy, we can say that this thing is less than equal to epsilon. Well, let me not skip a step. This upon h, but this is equal to epsilon h upon h, which is equal to epsilon. Okay. So what we saw is that whenever little h is in this region, this is controlled by epsilon. So fine, I mean, what we have shown is less than equal to epsilon, which is good enough, that it doesn't really change anything. So we have shown that whenever h is in this region, this quantity is less than epsilon, which shows right differentiability, and that the right derivative is f of c. So that's it. Right, so let us go over the details. This is what we wanted to show. Once you fix an epsilon, you want to find a delta such that whenever you hover from C in the right delta neighborhood, this ratio is at most epsilon. This is the definition of right differentiability, and saying that the right derivative is equal to that. So this is what we wanted to show, and then we looked at this quantity. We found out that that quantity is equal to that. So the absolute value of this quantity can be estimated as the upper estimated by this integral, and this we can further, because of right continuity, this value we have control over. So if this value is at most epsilon throughout some delta, throughout this region, then you can upper estimate this upper integral by this upper integral, and which is equal to epsilon. Okay. So yeah, so this is a theorem, and similarly you can prove that. And now let us go to what we like to call the fundamental theorem of calculus. Okay, so what we have is a continuous function. So then we will say two things: that there is a function capital F which is differentiable in the interior, such that the derivative of that function is equal to the original function throughout. The derivative at each point in this open interval is equal to the original function. So that's very nice. And the other thing is that these functions are unique in some sense. So any such f should satisfy this equation. So they're essentially unique. Once you choose what is the value of f of a, then you do not have any control over what the value of little x is. So you have just one small freedom in your capital F. And this is what we read in high school as integral of anything is whatever plus a constant. This is that constant. Okay, so okay, fine, we'll prove these two things. In fact, first we will show the existence of capital F by constructing it, and then we will show uniqueness. So define capital F as by writing f of x is the integral of f from a to x, and it is the integral because continuous functions are Riemann integrable, and therefore this integral makes sense. Okay, so we have that. We have defined something, and by the previous lemma we know that the derivative of capital F is little f for all x in a comma b. Immediately by the previous lemma. So, well, this shows 1. I mean, you can easily show that this is a continuous function. In fact, we have already seen that it is differentiable in the interior. For continuity, you just need to make sure that limit x tends to a of f of x. This is equal to f of a. But what is f of a? F of a is 0. So you need to make sure that this is 0. But that is clear because this will go to 0 as x goes to 0. Because f being a bounded function, f being continuous is of course a bounded function. So if you integrate over smaller and smaller regions, you'll get smaller and smaller values. So you can easily show that capital F is continuous everywhere because it is already differentiable in this interior, and at the boundary points you can show continuity by taking limits. Okay, so we have a continuous function whose derivative in the interior matches with the function little f. So we have constructed such a thing. Now we want to show uniqueness. So for uniqueness, basically to prove 2, let G be some other be such that G of G is continuous and differentiable on the interior, and the derivative matches with little f for all x's in the interior. So then what happens is then f as constructed above, f minus g has the following property. Has the property that f minus g is a continuous function differentiable on the interior and the derivative of f minus g vanishes in the entirety of the interior. So then by what we recalled in the beginning of this lecture, we see that this is constant. And that's it. That is what we wanted to show. We've expressed it a little differently, or apparently a little differently in this theorem, but the proof, I mean, if you just work it out, you'll see that we are actually proving the correct thing. The notation is a bit different in the proof than in the theorem. Anyway, so this is one enunciation of the fundamental theorem of calculus. Maybe this is not the most familiar one from high school, but this is one enunciation, and we will now go to perhaps the more familiar expression of it. So here is one way to state it. So start with a continuously differentiable function, and you can weaken this hypothesis. You can do with a little bit weaker hypothesis, but I don't really see the point of it. So I will prove it for this. So you have some continuously differentiable function. Then we claim that the integral of f prime, which makes sense because f prime is continuous, is nothing but fp minus fa, and I'm sure this we must have seen in high school. So philosophically it is saying the following: f prime is sort of like the local change in f, and if you integrate, integration is like summation. So if you sum up all the changes in f locally, you get the global change in f. That's what the theorem is saying. Okay, and why is this true? The proof is the following. So let little f equals f prime. Right, so what we have is f is continuous, thus f is continuous because capital F was continuously differentiable, so This is a continuous function. And capital F is a function which is differentiable, at least in the interior. It is differentiable, in fact, by hypothesis everywhere, but it is differentiable in the interior, and its derivative matches with little f everywhere in the interior. Not just in the interior, but everywhere. So I only care about the interior for my application. So thus f is a continuous function such that f prime x is f of x for all x in a comma b. Okay, and capital F is of course continuous by hypothesis. So therefore, by the previous lemma or theorem, we have f of x must be of this form. Right. So therefore, f of b minus f of a is fa plus integral a to b little f minus f of a plus integral a to a little f. This is 0, and this gives us integral a to b of little f, because that cancels out. Okay, so f of b minus f of a is that, but what is at the same time integral of a to b f prime is of course nothing but that by definition of little f. So these two things match. That matches with that. That's it, that's the proof. But whatever be the proof, this one should really think about it in the philosophical terms, that what you're doing is summing up the local change that turns out to be the global change. Okay, so this is very useful. So far we don't know how to integrate a concrete function. Suppose I give you a polynomial function and ask you to integrate it. It's not completely clear what to do, but this theorem allows us to find out those integrals. So here is one application. And so far we do not have a big repertoire of functions that are integrable. All we know is that polynomial functions are integrable because sums and products of differentiable functions, integrable functions are integrable. So we don't know many functions as of now which are integrable anyway. So here is, this also gives me an opportunity to introduce a notation. As we mentioned previously, that this thing, so this is, I'm talking something about the notation. So if f is a Riemann integrable function, then we write to mean the Riemann integral. So we have just introduced this dummy variable. Of course, instead of x you can use whatever variable you like. You can also use t or whichever variable you like. This is useful because suppose I have this function. Suppose I want to do this. Suppose I have this a comma b to r, which takes, let's say, x to x square. So suppose I wanted to integrate that guy. Instead of introducing this whole notation and saying, okay, you take the integral of f, what I can do is I can just write down a comma b x square dx, just like we used to write in high school. So it saves us all this trouble of introducing little f and then writing f, and so it's very useful. Okay, fine. So with that notation I want to give an example. So what we claim is that this integral is, as we all know, I'm sure, equal to that, but let us give a proof. So why is that? This is because if we let, just give me a moment. So let capital F from, I don't know what should be domain. Let me just define it entirely. Be defined as f of x equals x to the n plus 1 upon n plus 1 for all x. So we have defined that, and this is a continuous function, hence on every closed interval this is Riemann integrable. And in fact this is continuously differentiable, this function f. So okay, we don't care about its Riemann integrability, we care about its continuous differentiability. And since it is continuously differentiable in every closed interval, what we have is, by the previous lemma, we have that integral 0 to x of f prime is f of x minus f of 0. This is for all x, which gives us, we know how to differentiate this guy. This is a particular case of a polynomial, and the derivative is, we know what the derivative is. So this gives us 0 to x, x to the n. That's what the derivative is. I shouldn't write x to the n, this is t to the n dt. Okay, so this is, what is capital F of x? Capital F of x is x to the n plus 1 upon n plus 1, and f of 0 is 0. So we have that. So this is what we you know, how we integrate things in high school. Try to find a function whose derivative is the function you're trying to integrate. Basically, that is what this theorem tells us. Okay, so I will give a problem next time where you'll be integrating arbitrary polynomials. It's not much different from what we just did, but it's good to put it formally. Alright, so this is all that I wanted to say. As usual, like, comment, share, subscribe. I also have paid listening, and I'll see you next time.